Okay, good afternoon, everybody. So, this is the second live session of our course. So, hope you are all enjoying the course. So, today, briefly, we will actually, I will just take some maybe 5 to maximally 10 minutes to actually tell you a little about where in the cosmological context these things that we are studying is kind of important, and then I will take up your questions. Okay, so I will not go into the details of what is the kind of universe or what is cosmology, various things about cosmology, etc. But just tell you that presently all experiments actually indicate very very strongly that universe had a beginning and then it evolved with time, and we have the present universe now, and there are many things in it. There are galaxies, and galaxies as stars and planets, and in particular in our galaxy we have the solar system and ourselves, and then there are many things on earth. We expect that there are many things like that in other parts of the universe as well. Universe is expected to be homogeneous and isotropic from wherever, whichever point, and which means that there are no special points on this universe. It's not that we are at the center of the universe and then everything else is around us. That's not what is indicated by observations now. It says it looks like it is that we are just another point in space time in the universe, and every other point will see similar things. Of course, there are inhomogeneities when you look at small scales, but large scales it is homogeneous. So that's one of the things, and then with that, the cosmology was developed, and presently we think that what the model that we have given by the Big Bang cosmology is somewhat reasonable, and experimentally all the observations are consistent with it. So for particle physics, what's interesting in this is how all these things in the universe are firstly made, created, and later on how did they evolve. So this is basically, of course, apart from the gravitational interactions and then the dynamics in the cosmological, the space-time dynamics. Apart from that, particle interactions would have played a role in this evolution. All right. So what we think is that we can't go to the very beginning at time t equal to 0 or very close to that. We don't know. We don't have the theoretical mechanism to understand that yet. But about 10 power minus 10 power 19 GeV, or the Planck scale, energy scales, which corresponds to 10 power minus 43 seconds in the evolution of the universe in that way. That time onwards, we can actually think about and model the evolution of the universe. That's what in the cosmology we have been doing. Even there are many missing links. A lot of things that we are yet to understand. But particle physics, as far as particle physics is concerned, so um, there would have been some very high energy period even after the Planck epoch, which is 10 power minus 43 seconds, etc. Then there would have been some 10 power minus. So, as the universe is believed that the universe then expanded, and as it expanded, it cooled. The average energy of this thing came down, energy density. So, this means that at later times, the energy, corresponding temperature, etc., would be uh, smaller than the earlier times. So there are some times where the energy is 10 power 16 GeV or some such energies, which in particle physics corresponds to the grand unification scale, energy scale, where uh, there are theoretical expectations, although it is not confirmed or indicated by any of the experiments. These are some of the theoretical expectations, some nice features of quantum field theory or gauge field theory, which dictates the particle dynamics. So it kind of thing says that it's possible to actually think about, like we were thinking about electrostatics and magnetostatics separately at low energies. Then later on, we realize that it is nothing but the manifestation of the same electric charge, moving or not moving kind of thing. So if it is, that is a kind of a unification of electric and magnetic forces in a way. And similarly, then later on, electromagnetic interactions and weak interactions had to be considered together to understand the dynamics of particles at hundreds of GeV energies. So now, if you go further up into 10 power 16 GeV, etc., then it is expected that all these forces, strong, weak, and electromagnetic forces, would actually come down to together to, and maybe it is possible to actually understand this in a with a single kind of interaction, single type of interaction, and then for at low energies, this will evolve into seeing these electromagnetic interactions and weak interactions and the strong interactions separately. So that is at higher energy. So it is expected that in the earlier stages of the universe, even earlier to electroweak energy scales, there would have been a kind of a grand unification scale, etc. But we do not really have much of an idea, either experimentally or theoretically. Theoretical frameworks are there, but there are no experimental observations regarding that yet. Whereas the electroweak epoch is where we are actually currently understanding experimentally as well as theoretically very well the particle dynamics. So that means that we are at the energy scales of the current experiments like LHC, Large Hadron Collider experiments, which is in the TeV range or hundreds of GeV to a TeV range. So those energy scales are the electroweak energy scales. So in the electroweak, a lot of things that we have actually understood. We know how the particles interact at such energies. What are the gauge interactions? What are the basic interactions that we have? And mm, um, and what are the cross sections or what are the interaction strengths for various different interactions? We have also done experiments to test these things, and then all the experiments actually indicate that the standard model as the electroweak interaction as given or dictated by the standard model of particle physics is correct. There are some other something things which are not really beyond the standard model already, like the dynamics of the neutrinos, and yeah, at the moment that is one of the things that we can definitely say that we have we have clear indication that standard model has to be extended uh, to accommodate the neutrino dynamics properly, especially its tiny mass. Okay, so apart from that, it is consistent. The standard model is consistent with all various different precise measurements of many kind of coupling constants or the scattering cross sections of decay weights or the details of such experiments and everything. Okay, it is very consistent. So that part we understand very well. So that's where actually we have to apply one of the things that there is particle dynamics in the evolution of the cosmology. I mean, in the evolution of the universe. So, the rest of the how the universe would evolve, and then how various different structures like galaxies are ultimately formed after billions of years is kind of indicated or decided partly by the interactions of elementary particles at these early stages of the universe. So then further on, it is expected that, there's this very hot, dense quark gluon plasma stage. And that's another very interesting thing. I mean, it is the quarks are not really formed bound states like proton, etc. We now know, we have seen the quark model in our course. We saw that bound states of the quarks can be seen as physical particles, whereas quarks you don't see as free particles. For example, you have bound states called baryons as made of three quarks. Proton is an example, neutron is another example, and then you also have pions and other mesons, which are made of quarks and antiquarks. So this was just before this, meaning it was before such a bound state formation. Quarks were kind of expected to be free, not in a bound state, but freely moving around in things like in a plasma state. But it is not the electromagnetic plasma. It is not the ions and electrons, but it is the quarks and gluons. The color kind of charge is the one which is deciding the dynamics there. So it is called the quark gluon plasma. Okay, so we don't really have much of an observational evidence or measurements on that, but we are presently doing these experiments at the LHC. Okay, LHC we have apart from proton-proton collisions, in between we also consider the heavy ion collisions. So heavy ion collisions would actually give a lot of protons and neutrons which can come together at high energies, interact with each other, and then it is a dense state of matter. That is what is basically the what is needed for the formation of quark gluon plasma. So we can actually, we are expecting that we have some studies on this thing, but we don't really have much very clear understanding of this quark gluon plasma yet. But it is there, and then it is expected that we will know more about it in the coming years. And in the course, we are not really addressing this quark gluon plasma at all. It is slightly beyond what we can actually discuss at the moment. Whereas a little later, the quarks form hadrons and neutrons and protons and pions and other mesons. So that is something which we have discussed in our course. And there we know how many types of these things are there, what are the dynamics, a little bit, at least some kind of qualitative understanding we had in the course. Okay, so these things will be important at that stage of the universe, that is still less than, when universe is less than a second old. And as it further cooled down, then these protons and neutrons, now you have protons and plenty of these protons and neutrons. These protons and neutrons came together, cooled down, and then actually they came together to form bound states. And then we know that such bound states are called nuclei of elements. So there are single proton nucleus, and as a single proton with that is the hydrogen atom. Then the proton can combine with a neutron. You can get a deuteron, and then you can also have other isotopes of hydrogen. And you can also combine protons and neutrons, two protons and two neutrons, for example, to form helium. So these all these things were formed in at this stage of the universe. So it's again it's between 10 seconds to hundreds or a few hundred seconds, maybe 200 seconds or 300 seconds of the age of the universe. All these nuclei were formed. But not all of this, but only the light nuclei could be formed. That's again because of some things which we already learned. The nuclear dynamics is or understanding of nuclear physics is very important to understand the evolution of the universe at this stage. And it has far-reaching consequences. I mean, how well we understand our nuclear physics and how well we can actually look at what would have happened there, and then how many of this helium nuclei would have formed there, how many deuterium would have, I mean, no, deuterons would have been formed there, etc. So all those things will be decided by the nuclear dynamics, and a little bit of that we got exposure to. So we have looked at what is the deuteron, what is the dynamics there, what are the other nuclei, etc. But we won't be talking about the heavy ions or heavy nuclei here, because again, because of the certain I mean, if you look at the binding energy, then heavy nuclei could not be formed in this stage there. So early universe could only form hydrogen, helium, some of the other isotopes there of these light elements, and lithium a little bit, not much, and that's what it is. And then maybe a very trace of this other beryllium, etc. Okay, but nothing beyond that, because of the there's a gap between the energy binding energy of these elements and the carbon, for example. You couldn't form the carbon as such there. So they had to actually wait. I mean, where are these heavy elements formed? Heavy elements are formed in the interiors, inside the stars, or in the inside the stars, where there is gravity could actually help form or bring the energies to the level where heavy elements could be formed. Then there are also these supernova explosion, etc., where even heavier elements could be formed. All right. So that's how it goes. So understanding particle physics and nuclear dynamics is very important to understand the evolution of the universe. In fact, the Big Bang nucleosynthesis, it is called. I have written it as BBN, which is basically Big Bang nucleosynthesis. And this tells eventually how many. Suppose we measure the amount of such these nuclei which are formed at that stage are called primordial nuclei. So how many primordial, what is the amount of primordial helium or lithium or deuteron, etc., that we have presently? Okay, that will be decided by various things, including the number of protons, etc., that we have there at that time, and protons and neutrons, and also other nuclear dynamics. So, with all that, we could actually um, uh, get to know the evolution of the universe at that stage very well, and there are some issues that one has to resolve, which is basically, I mean, I'll tell you, name it, now, but in the next session, maybe I will explain a little more about it. One of the issues is this called the baryon asymmetry of the universe. It is basically saying that the whatever we see now, stars or galaxies or everything around us also, terrestrially as well, everything is made of these atoms, which are basically made of these protons and neutrons and electrons and nothing more. So what happened to all those antiparticles that we have been talking about, anti-neutron, anti-proton, etc.? Because according to our standard model, these particles or antiparticles are created in pairs. They would have existed at the same amount at some stage, early stages when they are created in that. Then in the evolution, something must have upset this symmetry, and then the number of baryons have kind of survived, whereas all the antibaryons I mean, could not survive in a way. So this is to be understood clearly. That is the baryon asymmetry of the universe, and this is still not understood very well. We will come to a little more details maybe in the next session. Then another thing is what is called the dark matter. So that also we will come to later on. Okay. So basically, I just wanted to actually put these our course and what we are discussing, the dynamics of elementary particles and the nuclear, the basics of this nuclear physics that we have been looking at in the context of this universe and in the evolution of the universe, where is it important, etc. So that some of you, if you want to explore further, you can go ahead and then do that. All right. And if anybody has any questions on all these things, or I'll be happy to take that up, and but not in the course as such, of course. But you can send me a mail, and the next class, next live session, as I said, we will tell a little more about what is dark matter and what is the baryon asymmetry of the universe, which are not really part of the course as such, but related things. All right. Okay. So that is what I wanted to tell in general. Now we can go to your specific questions that you have. So I will stop sharing and then go to your chat box. See what are the questions that you have there, right? Yeah, there's a question. Abhinav has asked a question, two questions. One is neutrinos were produced even before the atoms, just after the Big Bang. Yes, that is our understanding now. All elementary particles like electrons, quarks, antiquarks, positrons, muon, antimuon, all these things would have been, and all types of neutrinos would have been there much before the formation of the atom. I did not specifically mention what the formation of the atom. Maybe in the next one I can tell you that a little more. So after the Big Bang nucleosynthesis, there was a long period of time where we had to wait for about 400,000 years before we could actually um, get the neutral atoms. Okay, so this neutrinos were produced along with these other elementary particles like electron, etc., much before that, within very likely, yeah, during the gut epoch. Yeah, that is how it is. Is string theory correct? Well, we don't know. So far, there are no so far there are no experimental evidence for the existence of string theory. But it's a beautiful theory. I do not know personally much about string theory, so I won't be able to tell anything much technical about it. But my understanding is that it is a consistent mathematical framework to understand physics at very high energies. For example, beyond even the gut scale or closer to the Planck scale, etc. One of the things that we have been kind of ignoring in the particle dynamics, in the standard model and in particle physics beyond the standard model also, is the presence of gravity. So the gravitational interaction is too weak here. I mean, it will become important only in the at the energies of Planck scale compared to the electromagnetic interaction or other interactions. It will be very weak otherwise below that energy. So, but at such energies, such high energies, one has to actually consider the gravitational interaction, which means one has to, in fact, try to understand what's the quantum picture of the gravitational interaction. So far, we don't really have any consistent theory of gravity with quantum mechanics. Okay, we know quite well what is the classical picture of gravity. Einstein's general theory of relativity works fantastically well as a classical theory. And when we look at observe, I mean, when we look at objects which are big and where the quantum picture is not very relevant, so general theory of relativity works very well. And general theory of relativity is one of the key um, uh, one of the key ingredients in a way, or that that has gone into the cosmology that we know now. Okay, the Big Bang cosmology is developed with the help of or keeping general theory of relativity as as its framework, along with what's called the cosmic principles of isotropy and homogeneity. So it's certainly all right. It is working well. There is no problem. But when we want to actually go beyond Planck scale, or when we want to actually understand situations where quantum picture of gravity is important, there we don't really have any picture or any theoretical framework yet, which is tested. Where string theory actually gives one way of looking at it. One way of understanding quantum gravity is incorporated in string theory. The string theory basically tells that all interactions are arising from some one particular interaction. It unifies everything, and all objects can be understood as kind of excitations of some fundamental objects called strings. Okay, so that is how it goes in a very um, layman language. Okay, but we don't know whether any. I mean, is that the right thing physics wise or experimentally? Whether there is any indication, anything that tells us this thing? So far, no. It's not a fault of string theory in any way, because it is I mean, we have to actually find a way to come down from such high energy I mean descriptions, like what string theory is, to connect it with our low energy theory, I mean, experimental setups. So the experiments are running at very low energies compared to Planck scale, for example. So we don't really expect any much of the experimental, experimental evidence of string theory as such here. But there are a lot of people working in the phenomenology of string theory and then trying to understand how to connect it with experiments. Okay? But it is one of the very beautiful mathematical framework that we have developed. All right, I think I don't see many more questions. So if anybody has any questions, we can ask why neutrinos oscillate and why top quarks are so heavy. Yeah, this is another interesting. Both these are interesting questions. Neutrinos oscillate. The oscillation of the neutrino is in the sense that one can actually think about neutrinos of different types that we said somewhere in our course. I think it can be. Yeah, in last session also we mentioned this. Neutrinos can be of electron type, which is the one which actually is created or which is created in the beta decay. But there are also situations where we have, say for example, in the decay of pion, we can have muons and muon neutrinos, and that muon neutrinos are different from the electron neutrinos. So there are three different types of this thing: electron, muon, and tau neutrinos. And now this can actually, if they have some mass, quantum mechanically, it is possible to actually change the state from one state to one type of this thing to another state. So that's what is called the oscillation. Oscillation in the sense that, say, an electron type of this neutrino changes to muon type, and the muon type can change back to electron. So that is the kind of oscillation that we are talking about. Okay. So basically, the neutrinos, if they are to do this thing, then there should be a massive. If it is a massless particle, which will be like the photons, which will be moving with the speed of light all through, and then, they will not really be able to oscillate in a way unless we invoke some other interactions which are not really within the particle dynamics at the moment. Okay. So this is a generic feature of any kind of such neutral objects which have some mass, quantum mechanical objects. Okay. We don't need any quantum field theory to understand the neutrino oscillations. It's basically the feature of any quantum state which does not carry any charge as such. Okay. All right. So then, okay, the other question is about the top quark. Yeah. In fact, the heaviness of the top quark or the lightness of electron. Why some of the elementary particles are very light, whereas some others are very heavy. Like top quark is about 185 times heavier than the proton. It is an elementary particle, whereas proton itself is a composite particle. Whereas electron is as light as 0.5 MeV. So why is it so? We do not really have any understanding of this. This is called the mass hierarchy problem. Why are there hierarchy of the masses? We don't know. In standard model, we will see later that this is related to the Yukawa interactions. Yukawa interaction basically is the interaction of these fermions with the scalar fields. So top quark will interact with the Higgs field, the scalar field present in the standard model, and that interaction is the one which actually gives it the mass. So the Yukawa interaction is the one which gives the mass to the elementary particle as per the standard model. And those interactions has the strength of such interaction is not experiment. I mean, it has to be experimental. The theory does not prescribe or does not tell what is the strength of this interaction. It's given. It is a parameter which is not fixed in the theory. So it has to be obtained experimentally. So you have to measure the mass of electron, measure the mass of the top quark, measure the mass of the Higgs boson, measure the mass of muon, everything. Okay, so this is an experimental thing there, and but the problem is acknowledged that there is a hierarchy, and we don't know what causes the hierarchy. We are hoping that maybe when we go beyond the standard model and then maybe in the gut scenario or eventually in string theory or any such these things, perhaps we will get the answer. All right, so Vijay Kumar has a question. If there is any nuclear reaction occurring, let us say positive beta decay, then atomic number changes. That is, atomic neutrality is disturbed. Yeah, that is true. Neutrality of the atom is always disturbed. So whenever, I think we discussed this partly last week. If we think the whole mass. So what is produced there is not the atom, not the atom. It is the nucleus which is actually going to go away. So it will be ions, nuclei that will be formed. Of course, there is also, maybe we have to understand that it is happening in atoms. So there are these atomic electrons. So for example, when cobalt decays to nickel, then the cobalt decay is basically um, it goes to a different nucleus, and there are surplus of electrons there. And these when we consider the nickel, so it will be kind of, it cannot be always thought about that as that electron will be held together by or as an ion of the nickel. It's possible that way. It can also go away, and we have to consider the dynamics along with the that whole material in that this thing. So it's there. There is no imbalance in that way. The electron surplus of electrons will be there in that material. So that is what going to happen. Okay, and similarly for the beta plus also. So atomic electrons are not disturbed by this one. So initially and finally, the atomic electrons have to be the same, whereas the proton number changes. Therefore, in beta decay, for example, you have an additional proton. Neutron goes to a proton, and that means that an electron as a whole, there is an increase in the charge once that electron, the beta particle, is gone away from the material. So there will be an additional charge there. So the total charge will be conserved when we consider also the beta particle, electron which is emitted. But if you forget about that and then look only the rest of it, there is an imbalance in the charge. That will be there. Similarly for positron decay also. It will be the other way around. But that does not really affect the nuclear dynamics as much as, I mean, whatever we discussed in the course is a simplistic picture considering only the nucleus. But if there are very precise experiments, then one can actually understand the dynamics involving the atomic electrons. But that's very hard to actually model and then try to understand. One has to, I think there are a lot of research that's going on in that, and then there are at least people who are thinking about it, and then who have tried to see how these will disturb the atomic electron cloud, and then see how that will influence the motion of the particles which are emitted, etc. It will not change the neutrality as such, as I said, if you look at the whole thing. So you can't leave out what is emitted and then look at only the rest of it and then tell that there is an imbalance. There will certainly be an imbalance. It has to be there. As such, the total charge initially and finally, including the beta or beta plus or alpha particle, whatever is emitted, will be conserved. Whereas if you now ignore what is emitted, like electron or beta plus or things like that, if you look at only the rest of it, there will be a change in the charge, definitely. And that is to accommodate the charge of that emitted particle. So there is no problem as such. All right. Any other questions? If you have, maybe you can quickly type it in. Okay. Otherwise, I think thank you all. And yeah, we can discuss again things in the forum. Actually, in the forum, we can also, you can write down not only specific questions about the assignments or the course, what is there in the slides, etc. You can also type in this your difficulties or questions that is related to this, like what you are doing now. Okay, so we will take that up, no problem. So let us do that. Now we are going to get into slightly more involved particle dynamics, and then maybe you will have more questions there. So put it in the forum as well so that we can continuously discuss. Otherwise, we will discuss it in the next live session as well. Okay. So thank you all for the interaction and have a very good evening, and then I hope you will enjoy the rest of the course as well. Okay. Thank you all.